Hello everyone, this video is exceptionally good because we are talking about exceptional cases. These are inorganic chemistry theory based questions. These are based on the trends which they have MTA followed in past few years and this January shift paper as well. Okay, so let's get started with the first question which talks about the nitrogen family. I already told you hydrides of group 15, 16 are super important. Basically 15, 16, 17 groups are very much important. Okay, the first statement is nitrogen cannot form d-pi-p-pi bonds. Of course, there is no d-orbitals there. Due to the absence of d-orbitals, hence N triple bond N is very, very strong. Yes, that is strong. That's having 3 bonds over there, that makes it strong. And bismuth hydride is the strongest reducing agent among the group 15 hydrides. The stability of the group 15 hydrides starting from ammonia and then phosphine, arsenic hydride, antimony, and comes bismuth. So bismuth hydride is the least stable, which acts as a best reducing agent. Okay. The next one, nitrogen shows oxidation states from -3 to +5, but +5 state becomes less stable down the group. As we told, bismuth is always want to exhibit in +3 oxidation state because of the inert pair effect. So +5 state becomes less stable down the group, that is also right. And NCl₃ less stable than PCl₃ because nitrogen cannot expand its octet. So nitrogen cannot expand its octet because of the lack of d orbital over there, right? So d orbitals are not there, so it can't exist. So NCl₃ is unstable and explosive too, which makes PCl₃ is more stable. That is also right. So all are correct. This question, transition metal catalyst. Consider the following reactions catalyzed by the transition metals. Contact process, we have B2O5 and catalyzes SO2 oxidation. Haber's process, iron catalyzes nitrogen plus ammonia. Hydrogenation, nickel catalyzes, and Oswald's process, platinum catalyzes the ammonia oxidation. The reason transition metals act as a good catalyst is they can show variable oxidation states. They have partially filled d orbital that can accept and donate electrons. They can form interstitial compounds. They have high enthalpy of atomization. So first of all, variable oxidation state it has. That is a very important reason. So that's right. Then they have partially filled d orbitals. That's why it can accept and donate. That is also true. And they can form interstitial compounds. Interstitial compound is related to the hardness of the metal, right? It's not related to the catalytic property. So this is not right. And they have high enthalpy of atomization. It is related to metallic bonding again. So that is also not right. A and B are only right statement over here. Then dichromate oxidation products. But this type of question have asked in past papers like January shift paper. So K2Cr2O7 in acidic medium can oxidize different substrates as a substrate with the product. We know that K2Cr2O7 is a very good oxidizing agent, right? But in acidic medium, what is the change and how that reacts? So basically, this is the reaction. K2Cr2O7 plus 3H2S plus 4H2SO4 gives K2SO4 plus. Based on this reaction, they have asked 2 questions in different paper in past 4 days of test. So here you see H2S become sulfur, right? -2 oxidation state to 0 oxidation state. And SO2 is not giving anything. If I am talking about SO2, then I minus, that how that changes when K2Cr2O7 oxidizes H2S in acidic medium, the products are. That's what the question is. So sulfur, it's formed. Other than that, dichromate became Cr3+. This conversion that has been asked already. So yes and Cr3+. Question may be a bit lengthy and to confuse you, but very simple. Then consider the following complexes. Arrange the complexes in the increasing order of crystal flake splitting. This you very well know. I'm just giving you the spectrochemical series over here. You can solve it yourself and let me know the answer. Because time is very less, we have to do the questions, important and exceptional questions, very quickly. Let me know the answer in the comments. Then inner pair effect, the very important effect. Thallium in group 13 showing +1 oxidation state, lead in group 14 showing +2 oxidation state, bismuth in group 15 showing +3 oxidation state, and polonium in 16 showing +4 oxidation state, which is due to inner pair effect. So that is the question. So this we very well know, that is due to inner pair effect, and lead is also right. What about bismuth? I told you in the first question itself. And polonium shows +4 oxidation state, but it can show +2 and +4. +4 is not particularly stable over there, so which is a wrong statement. So A, B, C are only right. Coordination compound, a nomenclature type of question. This compound exhibits what are the isomerism? What is ionization isomerism? This coordination pair and ionization pair, that changes. So which can form a complex like this, right? H2O 5 times Cl with Cl. Right? I think .H2O must be there, should have been there. Then Cl can shift. Hydride isomerism, that can also possible. That is .H2O, okay. And geometrical isomerism, if I'm writing it like this, 4Cl2, which is A4B2 type. So that can show cis and trans isomerism. That is also possible. What about optical isomerism? Cis isomer may show optical activity, but trans isomer has the plane of symmetry. So that is not optically active. Not all the forms will show optical isomerism, so I'm just neglecting it. So 1, 2, 3 are the only right answers, considering all the forms are not showing optical isomerism. Which of the following statement about noble gas compounds are right? XeF2, XeF4, XeF6 are all stable compounds with linear, square planar and distorted octahedral geometries respectively. XeF6 reacts with silica to give XeO4, OF4. And these two are both powerful oxidizing agents, and with XeO4 being explosive, and xenon forms compounds because its ionization energy is comparable to that of oxygen. Okay, so tell me which of the following is correct about noble gas? XeF2, that is linear, that's right. XeF4, that is square planar. XeF2, that is linear, that is right. XeF4, that is square planar. XeF6, that is distorted octahedral, it's not a perfect shape. So which are all true. But what about statement B? It reacts with silica. So XeF6 plus SiO2, it forms XeOF4 plus SiFO. Okay, then this is also right. And XaO3 and XaO4 both are powerful oxidizing agents. Both are explosive too. So that is also true statement. Xenon forms compounds because its ionization energy is comparable to that of oxygen. That is not a correct reason because of xenon forming a compound. If xenon forms compound, it's because of the accessible d orbitals over there and the size is also big. Okay, so which makes these three are right. Then aqueous solution chromate ion converts to dichromate ion in acidic medium, and the reverse occurs in basic medium. That is true, and the conversion is due to the change in oxidation state of chromium from +6 in chromate to +7 in dichromate. So considering that, which statement is true or false? Okay, so first of all, in acidic medium what happens? This converts to Cr2O7 2- and H2O, right? In basic medium, that will become, this will become this again, right? So the first statement is true. And the second statement, oxidation state of Cr in CrO4 2-, that is +6, and here that will become +6. So if there is no change, and also +7 oxidation state, it can't exhibit +7. Manganese only exhibit +7. Okay, so which makes this is false. In a titration, 20 ml of 0.1 molar FeSO4 solution required for V ml of 0.02 molar permanganate in acidic medium. The volume V is, they have given what is the change happening over there. If in your exam they didn't give you what is the change, you must be able to know, you should be able to solve this problem, because we already told what is the change happens in acidic medium, alkaline medium, and neutral or slightly alkaline medium. Okay, please make sure you studied it well. So coming back to this question, so this is the balanced form. MnO4- 8H+, 5 electron gives Mn2+ plus 4 electrons, 4H2O. So what is the N factor over here? That is 5. It's because Mn +7 state to Mn +2 state it's going. So use the equivalence formula. N1V1 is equal to N2V2. They mentioned as a titration, right? So N1 into what is the N factor, and then into V1 is equal to M2 into Vn into V2. So substitute the values over here. 0.1 molar into 1, that's for FeSO4, +2 state to +3 state, into 20 ml equal to 0.02 into N factor here, that is 5 V. So by solving it, V will become 20 ml. So very simple question. Just you have to know is how to solve. What is the electron change happens over here? They have given here, but in exam most probably they won't give. Then halogen oxo acids. So here you see correct order of acidic strength. This question asked many times. So rule number 1, you have to remember, same halogen, more oxygens are strong acids. Same halogen, more oxygen means that is stronger. So the order HClO4, HClO3, HClO2, HClO, that is right. Next, same oxidation state, smaller halogens. Smaller halogen. For example, here you take this one, HClO4, HBr and HiO4. So which makes it stronger, so this is also right. Then other two, if you see, this is ulta, this is not right, and this is also not right. So A and D are only right. Match the following complexes with their coordination numbers and geometries. If you could match the coordination number, then other thing will come under the place. This is a separate question, this is a separate question. So just calculate the coordination number in geometry. This is a kind of match the following. There is an error, guys. So coordination number over here, that is oxalate. So coordination number is 6. This is 4, carbonyl, and this is 4, this is 6. And geometries, you can calculate it. That's not a problem. And coordination number and geometry of this one, oxalate, that is, I told you, 6 and octahedral. Actinides. All actinides are radioactive in nature. Actinide contraction is greater than the lanthanide contraction due to the poor shielding of 5f electrons. So let's say one by one, all actinides are radioactive in nature. So actinides are mostly radioactive in nature. Statement B says the actinide contraction is greater than lanthanide contraction. 5f electrons are showing the poor shielding, then 4f, that is also right. And actinides show higher oxidation states than lanthanides, and uranium showing up to +6. That is also true. Actinide shows +3 oxidation state to +7 oxidation state also. Okay, uranium itself can show +3, +4 and +5, +6 also. Then the last statement, the most common oxidation state of all actinides is +3, similar to lanthanides. So early actinides like thorium, protactinium, or uranium, neptunium, plutonium, they will show +4, +5, +6. Only later actinides are showing +3 oxidation state. So which is incorrect statement? They are asking incorrect, so D only incorrect. Consider the following statements of group 16 elements. So how the boiling point order changes. H2O, H2S, H2SC, H2TE due to hydrogen bonding in H2O. Due to hydrogen bonding in H2O, this is the order is formed. Okay. So hydrogen bonding is there in H2O, and it is having high boiling point also comparing others. 100 degrees Celsius, but weaker one is H2S, that is -60 degrees Celsius. So which makes it right. And bond angle decreases in the order due to decreasing electronegativity. H2O is having the degree bond angle 104.5. And H2S is still lower than that, 92 degrees, and then H2SC and H2TE are lower than that. So that is also right. And SF6 is kinetically inert, while Cl6 does not exist due to the larger size of chlorine. Yes, Cl is a bit larger and it will create a steric hindrance. That's why it is not forming, but fluorine is smaller in size, so it can form. Then oxygen shows oxidation state from +2 to -2, while sulfur shows -2 to +6. Basically, oxygen cannot expand the octet. Maximum +2 only it can show. Only in OF2, you remember, that will show -2 oxidation state. But typically it will show -2, -1 and 0. Right, in elemental form. In case of sulfur, it can use the d-orbitals. Right, it can use the d-orbital, which can able to show -2 to -6. So statement D is also right, considering OF2. Hydrogen, the complex nickel cyanide complex is diamagnetic while nickel chloride is paramagnetic in nature. Cyanide is in strong field ligand, chloride that is a weak field ligand. This is diamagnetic and that is paramagnetic, true. And Cn minus, okay, while weak field ligand, that is also true. So both A and R are true. Okay, the next one, which of the following pairs of elements have nearly identical atomic radii despite being in different periods? So this is an easy question though. Zirconium and hafnium. Sometimes what they will do, they will twist you with these type of questions from in lanthanides also. After lanthanide, atomic number 57, the 4f orbitals are filled. So it will give you very poor shielding effect, right? So that will cause the contraction, lanthanide contraction. Due to that, what will happen? Zirconium and hafnium will have almost the same size. That is 159, another one is 160. Right? And also if you see niobium and tantalum, that is also 146 picometer. And molybdenum, tungsten, that is 139 picometer. Iron and ruthenium, that differs. Iron is 126, ruthenium is 134. So there is no lanthanide thing over there. So which makes A, B, C only right. Again, K2Cr2O7 reacts with FeSO4 in acidic medium to produce this one. This is true. And heating with KCl and concentrated sulfuric acid liberates chlorine gas. Okay, and K2Cr2O7 reacts with H2O2 in acidic medium to form blue color peroxochromate. Okay, and K2Cr2O7 reacts with NaOH to form this without any change in oxidation state. So if you see the first statement I told you, that is right. The second statement, I'll give you the reaction. It may be helpful for other questions as well. O7 plus 4 KCl, KCl or Ki, whatever they are asking. This goes like this. K2SO4 plus Cr2SO4 twice and Cl2, then H2O. Okay, it liberates chlorine gas. And with H2O2, it is forming peroxochromate. We saw this in one of those mock test paper, the butterfly structure kind of thing, right? So that is also right. And this we just now saw, there is no change in oxidation state. So that is also right. Gallium has higher oxidation state. Okay, first of all, first ionization energy of elements in group 13 follows the order this. This trend is anomalous because, okay, so gallium has higher oxidation state, ionization energy than aluminium due to the presence of completely filled 3d orbitals which provide poor shielding. So gallium configuration, if you see, that is after argon 3d10, 4s2, 4p1. Okay, so this filled 3d10 will shield it. So that makes it poor shielding. Effective nuclear charge becomes higher than the expected. That's why this statement becomes true. And the expected trend should be barium, aluminium, gallium, indium, thallium. Based on the atomic size alone. Okay. So based on the atomic size alone, we can expect that. But due to the other reasons, it is not following that. Okay. Then the anomaly is due to inert pair effect becoming the predominant from aluminium onwards. So that is not starts from aluminium, it is starting from thallium. Okay, so which makes it the wrong statement. And statement D says aluminium has lower ionization energy than gallium due to the larger atomic radius because of d block contraction effect. Okay. Then isomerism part, again So you can see A5B type with SO4, they are just asking for geometrical isomerism. This is an octahedral and 5 identical ligands are there, so which can't exhibit geometrical isomerism. The next one is paired planar and cis-trans isomerism are possible over here. And this one is A2B2 type, which can also show. It's not A2B2, it's AA2B2, octahedral. Then A3B3, which will show FAC and meridonial, facial and meridonial isomerism. Okay, so these can exhibit geometrical isomerism. Potassium permanganate oxidizes oxalic acid in different media. Identify the product of Mn obtained in each medium. This I told you before. Right? So I'm giving you the reaction. With oxalic acid, it goes Mn2 plus. Mn plus 7 state to Mn2 plus state, pink to colorless state it changes. And in alkaline or neutral medium, slightly alkaline medium, it changes from MnO4 minus to MnO2, where it's showing a brown precipitate. Okay. Then alkaline medium, it will give you MnO4 2 minus, that is a green solution. So the changes are Mn2 plus, MnO2, MnO4 2 minus. Very, very, very important question. Which of the following statements are correct about lanthanides? The ionic radii of lanthanides decrease steadily from lanthanide 3 plus to lutetium 3 plus due to lanthanide contraction. Yes, that is true. From lanthanum 3 plus, that is 103 picometer, and lutetium, that is 86 picometer. That is true. And lanthanide contraction is due to impaired shielding of 4f electrons. The 4f electrons will show the poor shielding. It's due to their diffused shape, that we know. Then cerium 4 plus is a strong oxidizing agent, while europium 2 plus is a strong reducing agent. So cerium 4 plus, if you consider, it can go to cerium 3 plus as well. Right. So that can act as an oxidizing agent. And europium 2 plus, if I consider, it easily get oxidized to europium 3 plus. So 3 plus will act as a reducing agent. 3 plus will act as a reducing agent, and 2 plus will act as an, okay, they are asking 2 plus is a reducing agent. The 2 plus is not a good reducing agent. 3 plus is a good reducing agent. So, which makes this is partially right. Then all lanthanides exhibit +3 oxidation state and their compounds are generally colored. So, it's not true. All the compounds are not colored. It's from lanthanide, it's colored because of FF transitions. Okay, so lanthanum 3 plus, like 4F0 configuration, that is colorless. Lutetium 3 plus, that is completely filled configuration, that is colorless. So we can't say those are colored. Okay, so that is also false. Potassium permanganate on heating at 573 Kelvin forms potassium manganate. So upon heating, what is the change happens over here is KMnO4 gives K2MnO4 plus MnO2 plus O2 at 573 Kelvin. So which will form manganate. So that is true. Both potassium permanganate and potassium manganate are tetrahedral and paramagnetic in nature. So permanganate, that is tetrahedral. MnO4 minus. That is tetrahedral, Mn which is in +7 oxidation state, and this is in diamagnetic. There is no unpaired electrons because of +7 oxidation state, no? So 3D manganese, that is 3d5 4s2. All 7 electrons are gone. So obviously that is diamagnetic in nature. Then potassium manganate, if I say, that is also tetrahedral, and which will have, see the oxidation state, MnO4 2 minus. So which will make it +6 oxidation state. So there is 1 electron, that is paramagnetic. So although that is a tetrahedral, but that is not an, this is paramagnetic, that is dia. So which makes this is wrong and this is right. Following statements are correct about lanthanides. The ionic radii of lanthanides decreases steadily from lanthanum to lutetium due to lanthanide contraction. That's right. Lanthanide contraction is due to imperfect shielding of 4f electrons. Yes, poor shielding of 4f electrons. That is also right. Cerium 4+ is a strong oxidizing agent. Europium 2+ is a strong reducing agent. So if you see cerium 4+, that can go to cerium 2 also. Cerium 2+ also by gaining electrons, right? So itself get reduced so that it can oxidize others. Talking about europium 2+, europium has a configuration of, after xenon, 4f7 6s2. So europium 2+, that is 4f7 6s0. So this half-filled configuration isn't quite advantage, right? It is much more stable compared to other 2+ lanthanides. But if you see europium 3+, that is Xe4f6, it is more stable because it's already in the most stable oxidation state of this series. It has no strong tendency to lose more electrons, right? So even gain electron also. So comparing 2+ and 3+ state, 3+ state would be much more stable for europium than the 2+. So which can act as a strong reducing agent. And the fourth statement, all lanthanides exhibit +3 oxidation state and their compounds are generally colored. Not all lanthanides. If you see +3 of lanthanum 3+, that is F0, and lutetium also completely filled, so those are colorless. This is a wrong statement. All 16 elements, group 16 elements form oxides. Generally formula is EO3 and O2. Both types are acidic in nature. Not really. Sulfur SO2, SO3 are acidic, true. Selenium SO2, SeO2, SeO3 are acidic. But talking about tellurium, it's not so acidic. It becomes amphoteric in nature. Tellurium oxide, tellurium O2. And polonium also, it's towards the basic. Okay. So which makes it wrong statement. And statement B, tellurium oxide TeO2 is an oxidizing agent while SO2 is a reducing agent. Yes, that is true. SO2 is go to SO3 as well. And statement C, reducing property decreases from this to this. It's not decreases, it increases. So which makes it wrong statement. Decreasing order of atomic radii, thallium, indium, gallium, aluminium, boron. So the actual order must be thallium, indium, aluminium, gallium, boron. Right, because of gallium is less than aluminium due to the d block contraction. Right, we saw already in one question. And statement B says down group 13, electronegativity decreases from top to bottom. So electronegativity decreases from top to bottom. That is true, that is a general trend. Boron is more electronegative and thallium is the least electronegative. Aluminium dissolves in dilute hydrochloric acid and liberates H2, but concentrated nitric acid renders aluminium to passive by forming a protective oxide layer. So that is also true. The passivation happens for nitric acid. That is also true. Then all elements of group 13 exhibit highly stable +1 oxidation state. This is a false statement because aluminum shows +3, that is more stable. So that is not correct. Then statement E, hybridization of aluminum in this complex is sp3d2. So that is true. It is forming an octahedral complex of 6 water molecules. That is true. Stability decreases in the order of ammonia, phosphine, arsenic, antimony, bismuth. That is true. And reducing ability increases in the order. Yes, bismuth is having more reducing ability. We saw already among the hydrides, NH3 is strong reducing agent while BiH₃ is a mild reducing agent. This is false. Quite opposite is true. Okay, this is false. And basicity increases in the order. This we already saw. Basicity increases in the order of nitrogen. That should come first. Then comes phosphine, arsenic, antimony. So it decreases down the group. Group 14 elements A and B have a first ionization enthalpy values of 708 and 715. Above values are lowest among their group members. Nature of the ions A2 plus B4 plus respectively. Okay. So let's see step by step. Group 14 elements, carbon family, right? So carbon, silicon, germanium, tin, lead. They said 708 and 715. So the matched values over here, that is belongs to tin and lead. Okay, tin is 708 and lead is 715. If you know that table there in the NCERT, you can solve this question. I'm talking about the nature of their ions. A2 plus and B4 plus. A2 plus, that is tin 2 plus. Tin 2 plus, after losing 2 electrons, it will become 4d10 right? So it can act as a reducing agent, so it can oxidize to form 4 plus state. Okay, then what about oxidizing nature of lead? Lead 4 plus. So 4 plus is there, so which can go to 2 plus state, right? Then this complex observes at lower wavelength of light with respect to this complex, this assertion, and the reason is wavelength of light observed depends on the oxidation state of the metal ion. So if you see the overall charge, that is +2, so the oxidation state of cobalt is +3 here, right? And here if you see, that is 3 plus state, water is neutral, ammonia is also neutral, so that will become +3. Both complexes of cobalt have +3 oxidation state only. Talking about the ligands. In the second complex, I have both are neutral ligands, and this one I have fluorine. So according to the spectrochemical series, you can see this as an order. Cl is a weaker ligand, then the H2O. So weaker ligand means what will happen? The splitting will be smaller, right? So smaller splitting means it absorbs low energy. Absorbs low energy means what? Longer wavelength. Correct? So this absorbs lower wavelength is wrong. It absorbs longer wavelength, not shorter. Okay? And the wavelength of light absorbs depend on the oxidation state of the metal. That is also true. It's depend on the oxidation state of the metal, nature of the ligands, geometry. Those are the reasons. So the reason is true, but the assumption is false. Iron 3 catalyzes the reaction between iodide and persulfate ions in which A it says Fe3 plus oxidizes the iodide ion, Fe3 plus oxidizes persulfate ion, Fe2 plus reduces iodide ion, Fe2 plus reduces persulfate ion. Choose the most appropriate answer. So let's see one by one. Before that, I'll give you the reaction. So Fe3 plus 2Fe3 plus 2I minus gives Fe2 plus I2. So which means Fe3 plus oxidizes the iodide ion, right? And talking about thio, Fe2 plus S2OA2 minus gives 2Fe3 plus 2SO4 2 minus. So Fe2 plus reduces persulfate ion to sulfate ion, right? So the first statement, ion oxidizes iodide ion, that is right, and Fe3 plus oxidizes persulfate ion, that is false. Fe3 plus is not directly reacting with a persulfate. Then Fe2 plus reduces iodide ion, that is also false. Fe2 plus reduces persulfate ion, that is true. Okay, which of the following is correct about zinc, cadmium and mercury? They exhibit high enthalpy of atomization as D subshell is filled, and zinc and cadmium do not show variable oxidation state while mercury shows. Compounds of zinc, cadmium, mercury are paramagnetic in nature. Zinc, cadmium, mercury are called soft metals. Okay, so first talking about high enthalpy of atomization. These metals actually have low enthalpy of atomization compared to other transition metal elements. Because you see zinc, that is after argon 3d10 4s2 configuration. Cadmium after krypton 4d10 5s2 configuration. Mercury after xenon 4f14 5d10 6s2 configuration. So they are having filled d orbitals, but they don't participate much in the metallic bonding because other electrons are there. So that will have low enthalpy of atomization compared to others. Zinc and cadmium do not show variable oxidation state while mercury shows. Yes, zinc, you see, that can lose these 2 electrons, zinc and cadmium, but mercury can show +1 state, +2 state, right? And then statement C, these are paramagnetic in nature. They all have filled D10 configuration and there is no unpaired electrons over there, which means they are dia, not paramagnetic. They are all soft metals. Yes, they are all soft metals. Highest oxidation state of manganese in exhibited in Mn2O2. The correct statement about Mn2OR. This is not O2, this is O7. O7. So manganese is tetrahedrally surrounded by oxygen atoms. Manganese is octahedrally surrounded by oxygen atoms, contains MnO, Mn bridge, and Mn bond is there. So let me draw the structure of this Mn2O7, which is, you see, these are tetrahedrally surrounded. Right? And it contains Mn bond, that is not true, and it contains MnO, Mn bridge, that is correct. Tetrahedrally surrounded by oxygen atom, that is right. Other two are false. Then identify the incorrect statement about PCl₃ from the following. So if you see PCl₃, in this molecule, orbitals of phosphorus are assumed to undergo sp3 dehybridization. Yes, that is true. Geometry of PCl₃ is trigonal pyramidal. That is also correct, right? because the structure look like this. Right? Then PCl₃ has two axial bonds are stronger than three equatorial bonds. The equatorial bonds of PCl₃ is lie on the plane. This statement is right. The three equatorial bonds of Cl, that is on the same plane with the bond angles of 120. If you see the equatorial bonds, axial bonds, they are not stronger. So that makes it incorrect statement. So these are all true. Practice more questions. Let me know what type of questions you want next.